Good afternoon, everyone. Let me know if you can hear me and can see the screen.
Yes, sir.
Thank you. Let's start our discussion. Today we'll look at the protocol that is used to communicate routing information across the different autonomous systems. And by implication, the same information is also communicated within the autonomous system. The primary issue with the intra-AS routing and protocol we studied is we looked at the scaling and autonomy, which can still be looked at in terms of cost otherwise. But key challenge that the intra-AS routing like RAIP, OSPF, VTC does not address is what is called policy challenges. Consider that we have different AS, let's say I have AS1 and then I have ASX, I have ASY, you have ASZ, okay, let's say ASP, so on and so forth. And they are all connected to it. We have connectivity. Now in this, AS1 can send traffic to Y either via Z or via X. Now AS1 can define a policy that if you would like to send any traffic to Y only via X or anything else, or I would say can't send traffic to Y but not from X to Y directly. So basically saying I would like to send traffic to Y directly without X, with X, or something else. So this kind of policy is not supported in your any of intra-AS routing. Further, what my policies are, we keep it to myself. We don't publicize it. They're my policies, and we like to honor those and implement those. In fact, we could have even more complex policies that for a given place, let's say I am X and I'm connected to Y and also connected to Z. And I want to use Y only for destination R1 and R2, and even though Z could reach and the other destination, let's say R3, which even Y could reach and Z could reach, what we are saying, we will use Y only for R1 and R2 and not for anything else. And this kind of decision making is defined by policy and could be any complicated. And we could define what needs to be done. I could say what route I reachable, I may advertise, may not advertise. And these are the issues that is not addressed by intra-AS routing such as OSPF. Further, look at the OSPF or RAIP or any distance vector or linkage category. Both these protocols make use of what is called a link cost. Now, if they are within the same domain, then I can define what my link cost is. Just to give an analogy, let's say there's a section A and section B, and section A is one subject, same subject is taught by two different teachers, and teacher 1 gives marks out of 100, teacher 2 gives marks out of 10. Now the different scale, if you want to now define who is the topper among the two sections, can you really use those marks? Because teacher 2 has given mark out of 10, teacher 1 out of 100, those marks are not comparable but to look within that context. So within the class B or class A, you have to look at who is the best and then probably do comparison. But if you want to look at pure marks, you can't even compare. Or other example could be, let's say I want to measure the tall students, percentage of whatever tall students. And one class I measure height in centimeters. In other class, I measure the height in inches. Then again, the two cannot be measured because my cost is the absolute number. We don't give dimension to it. And that cannot be comparable. Same way, if I look at AS1 and AS2, if my AS1, let's say all the S cost starts with 100, and in AS2, all the cash starts with 1, 2, 3 lower numbers, and depends on 1.1 or something of that kind. Now, if we need to define reachability, so this cost value 100, 200 has no meaning because its scale factor is a 1 or 2, and that will simply confuse. So that means if we were to look at the path cost as we've been doing in our distance by OSPF other, they are not applicable because different autonomous systems may use different criteria for defining a cost. And that means we need a different category of protocol for our routing reachability across different autonomous systems. Another issue that needs to be looked at is what is called an issue of trust. Let's say I am autonomous system 1 and there is an autonomous system B. And system B has different networks, let's say X1, X2, X3. Now, this B is advertising to me not only X1, X2, X3, but it also maliciously advertises me Y1, Y2, and other networks, even though they are not there. Now, B advertising me that I can reach X1, X2, X3, Y1, Y2. How does A trust that what B is saying is right? Does it trust everything what B is saying? Does it trust partially? Or what the criteria it can basically use? Or even A says I can trust X, A says I can trust B only if it trust advertises X1 and X2. Because I know that X1 is connected to it. If it advertises that, then I know it's trustworthy, otherwise it is not. So primarily what we're saying is, what somebody advertises, how do you trust or do not distrust? If somebody doesn't advertise, somebody falsely advertise, somebody do only some advertising, not completely. So issue is cannot use the cost because we use different parameters. So what kind of protocol we need because our intra-AS routing, such as RAPE, OSPF, which belong to category of link state and distance vector routing, those cannot be used. And that is where a new protocol called BGP, which stands for Border Gateway Protocol, that is used, and BGP is default protocol that is said to glue the entire internet together. So all the autonomous systems in the internet, they talk only one protocol when communicating with each other, which is BGP. What BGP does is it propagates reachability across the AS, and so it basically propagates reachability across the neighboring AS systems, and also within the autonomous. Once I get information from my neighboring AS, but within the autonomous system, it also propagates, and we'll shortly look at how does it do. Both distance vector and link state routing make use of cost, and we said cost could be different by different administrator. Cost cannot be used. That means BGP doesn't belong to neither distance vector nor to link state routing, but it belongs to the next category, which is called path vector routing. What it means is, whenever we advertise a list of autonomous systems autonomous system A, autonomous system B, autonomous system C, and that kind of becomes a path vector without a cost. We only tell reachability which are the autonomous systems and which are the destinations reachable through this list, but without any giving a cost idea. And because we are giving a path of autonomous systems, in that sense, this protocol is called path vector routing. One of the key things we require from this BGP protocol is support for policy decisions. Of course, the fundamental requirement of any routing protocol is it should not give me a routing loop. Routing loop meaning it should not happen that once I build a routing table for a destination, A gives a packet to B, B gives to C, C gives to D, and D gives back to A. That becomes a routing loop. So we should be able to avoid routing loop. It should be able to honor policy decisions as determined by the network administrator, and it should propagate reachability information across AS and within the AS, and that's the protocol we look at BGP. So let's look at, in principle, how does BGP really works. So three autonomous systems, AS3, AS1, and AS2. AS3 is connected to other network, so AS2 is connected to another network. Now 3A is the gateway, and so is 1C. So AS3 gateway router 3A sends a BGP message to 1C, router 1C of AS1, indicating which are the networks reachable via itself, which is AS3. Now AS3 can aggregate, let's say it has number of network reachable. For example, one network happens to be 10 dot, let's say 1.0.0 slash, let's say 16. Other network is 10.0.0.0 slash 16. So this is one network which is 10.0.0, is another network which is 10.1.0.0. Now these two networks, either I advertise separately, but both of them come through me. To reduce the number of routing entries, both of these networks can be aggregated into a simple network, which will become 10.0.0.0 slash 15. So two network entries could be combined into one, and that could be that this is what is called aggregation. So it can aggregate to reduce the number of routing entries, and further, it should also support something called stub-AS. Stub-AS meaning the autonomous systems which are at the end, which are not transit. So those AS which either originate traffic or consume traffic, they do not carry any other traffic through it. Shouldn't happen that AS3 sends traffic to this network and this fellow sends to something else. So that is the meaning of stub network. Either they originate or they consume. So BGP should support that. So typically BGP messages are of two kinds. They call eBGP and iBGP, which will come in a short while. So BGP basically sends BGP message or what is called a semi-permanent TCP connection. Semi-permanent TCP connection means that once the 3A and 1C establish a TCP connection, it remains forever. And if any point in time the connection breaks, and BGP will send a message, this point connection is break, it reestablishes the connection. Otherwise, it tries to use the same connection. So once the connection is established, this connection is not terminated. It remains on forever because you'll be sending BGP messages. But if it is found to be broken due to whatever reasons, then same connection will be established again. And that's the meaning of semi-permanent connection. And that's the way BGP works. Now, BGP, as we said, works across two places. One is between the autonomous systems. That is where they understand reachability of each other. And within the autonomous system, it has to propagate. It can also do the aggregation, consider the full network. one network, second network, 138.16.65, 16.66. All these four networks can be combined into one network, 138.16.64/22, and that's the prefix that could be communicated. That means we combine all them into single network, and that will help me reduce my entry. So we like BGP to aggregate. Even with this aggregation, if one of the network moves away, because we have a notion of longest prefix match, those who've forgotten longest prefix match, I would recommend you to read about it, refresh your routing concept, and basically means for a given destination, there could be two different networks. So we look at which network has a longer prefix, and whichever longer prefix is there, in this case, packet would be routed to the longer prefix, and that's the meaning of, so BGP supports that as well. So let us look at how do we distribute the path information across different autonomous systems. So 3A would basically indicate all the reachability network within itself, network what is connected to, and 3A would indicate to 1C that these are the networks I could connect to. So look at the connectivity between the ASs, the connection is shown via solid line. And same thing, because same BGP is used, look at this reachability within the router about autonomous systems. So each router sets up a TCP connection with every other router within the autonomous systems, and that is called iBGP, and these are shown with dashed lines. So we have two kinds of BGP connection. One is called eBGP, external BGP. Other is iBGP, which is internal BGP. So eBGP is used to propagate reachability information across the AS. And then when 1C receives, it uses iBGP to propagate the same reachability information to all the other routers. And once router 1B receives, which is the gateway router, it will use eBGP to connect reachability of what network it learns to the AS2, that means to the router 2A, and then 2A would propagate the same information using iBGP to other routers within the autonomous systems. And while sending it, it can even do a prefix aggregation, summarization to reduce the number of routing entries in a routing table. Because if you do not do aggregate, the number of entries could be much large. So in other, if you look at this OSPF or the link state, other routings, we send the network information, no aggregation, and number of entries could be large, but here we could do aggregation, and that way, even though internet is millions of networks and routers, a router would not have millions of entries, but much less because of number of networks are aggregated into one. So what is the information that BGP propagates between one router to the another? It basically advertises what is called a route, which consists of prefix. Prefix meaning a network destination to which traffic should be sent, and the attributes. So prefix is the network destination, for example, 10.1.1/22 or 21 or whatever. So prefix is the network destination address, and attributes is basically related to the BGP information. There are many attributes, but to look at the only main ones which are applicable to us for our course. One is called AS path. It basically gives me a list of all the autonomous systems which are needed to reach this destination. So basically it will contain path AS2, AS1, and prefix X. So each time, let's say, it goes to AS3, when AS3 advertises, it will become AS3, AS2, AS1. And now in this process, when you keep advertising, if I receive some information which contains my own AS, for example, let's say I am autonomous system A, it gives information to autonomous system B, B gives to autonomous system C. So let's say there is a network reachable, which is just prefix X. So A will send to B, that path is A and prefix is X. Now when B sends this information to C, it will basically say B, A is the AS path and prefix is X. When C sends it, it will add its own prefix, so it will advertise C, B, A, X. And this way it comes, if somewhere A receives this, it knows that I am in the path itself, that means this has become a routing loop. So if any receiving autonomous system receives its own AS in the AS path, it knows it is a cycle, and then it rejects the advertisement because it has already communicated that the prefix. So other thing that the BGP route contain is what is called a next hop. And we can explain with an example with few figures down the line so that I know if I have multiple hops, which hop I should use to advertise or to send packet to my internal routers. And once we have the route advertised received through the gateway routers internally, we make use of what is called import policy, whatever policy we have defined to accept or decline. We can say the neighboring AS will accept the route advertised only if it contains some other routes or it doesn't contain some routes and whatever that is, and that way we can determine and define the policies. So primary goal of BGP is support policy-based routing, and this policy-based routing could get too complex, but we'll keep it simple for our understanding purposes. So typically, when an internal router receives multiple AS paths for a particular network prefix, how does it select? A well-defined rule, what is called a route elimination criteria or route selection criteria. First of all, each destination, a network admin can configure what is called a local preference. And local preference has the highest value. So anytime you look at the decisions, you look at what is the local preference value for this route, and whichever is the highest, we basically give that path and nothing else. If for route we get two different places and we get the same local preference, then they look at the two AS path. One could be from gateway A, other could be from gateway B, and look at which gateway has a shorter AS path to the destination, and we look at that gateway that has this shortest AS path destination. If the two different AS paths have the same link length, then we do what is called a hot potato routing. That basically means I have two gateways, let's say from a router 1B, one gateway is 1C, other gateway is 1D. Then using my intra-AS routing, I determine the cost to 1C and 1D, and whichever router has a lower cost, I choose that as a next hop, and that is what is called a hot potato routing. And if even that is same, the two routers are the same, then we can resolve it by a tiebreaker called BGP ID, and that could be. And in that sense, BGP routing policy. Now we'll take a few examples. How does BGP implements policy-based routing? Let's consider we have 6 autonomous systems. APC, which are called backbone peer ISPs, and other is WXYZ, which are called the customer network, or that means these autonomous systems, they either receive traffic, which they consume, or they send traffic, that means they originate. So X cannot be used to transit. X would not like that when B sends a traffic to C, B should send to X and X should send to C. Because if that happens, X is become a transit network, where X is a customer network. X should only receive traffic for its consumption, so send traffic what originates, and it should not transit traffic from other. Given this criteria, how does BGP works to implement this kind of policies? As you said, we look at 3 WXYs are customer-centric networks, which can also treat as stub AS, and ABC we can look at provider networks, which are the backbone networks which connect to each other. Now X is connected to both B and C, and we do not want that X should send traffic from B to C. If B has a traffic to C, B should send directly and not to X because X is a stub network. So what happens typically is, let's look what will happen. That means whenever X advertises to B or to C, it will only advertise X, it will only advertise X to C. X will not advertise XC. So when C gives the information, it will say C. When B gives the information, it will say B. If it were to advertise the same, this B has given a path sub destination. When X advertises, it should not say BX. Because if it gives the path BX to C, that means it's telling C, I can reach a destination, some destination via me to B, and that means C can use that X as a transit. That basically means X should only advertise itself. It should not advertise any other destination received from other provider networks. So if B sends a route called CAW, that means W advertises becomes AW. So A would send to C called AW. C advertises to X, which becomes CAW to both X and Y. So now X receives CAW. X should not advertise XCAW to B, because if it advertises XCAW to B, then B can send traffic via this route to W rather than showing directly, and that's what the policy decision would be. So even though X would receive CAW, X would not send XCAW to B either. In the same process, X would not advertise WAB to C either. Or X would not advertise BAW to C, X would not advertise CAW to B, and because it is not advertising that, it only acts as a stub network. That means it either originates traffic or terminates traffic, but not both. Can X advertise XCY to B? Look at here. Y gives path Y to C. C would give a path CY to X. Now, should X advertise this XCY path to B? It should not. Because if it does, then B can send traffic for Y via the X, which goes via the C, whereas B should send traffic to C with the provider network at the core level, and they shouldn't be using other one. And these core providers, they have their own peer level agreement to talk to each other and normally means send traffic directly. So X should not advertise XCY to B. It should only advertise X to B and X to C, and that's the way it works. Same way, when A advertises path AW to B, should B advertise this path BAW to C? It should not. Because if B advertises path BAW to X is fine, because if X needs to send traffic to W, X can send to B, A, and that's where it goes to. But B should not advertise the path BAW, this path to C, because if C receives this path, then for a traffic to W, C can send via this path rather than sending directly. So because of peering network at the same level, B should not advertise path BAW to C, and that way they implement policy. And same way other one, at times B wants to force C to route to W via A, which is not the case. So because if it advertises, that is what would happen. So to implement a policy, you basically decide what kind of path you would like to advertise. By the same logic, should C advertise to B the path CAW? Any questions? Assuming we are the provider networks and they should not use anybody as a transit network. So question I am asking is, should C advertise the path CAW to B?
No, sir.
No, because then it becomes C becomes the transit.
That's clear, yes.
Yeah. Other one, should C advertise the path CAW to X and Y? Question is, should C advertise the path CAW to X and to Y?
Yes, sir.
Yes, because X may want to send a traffic to W, then X should know to go via C. But now X can have a policy decision that any traffic to W, it will like to send via B and not via C. And that will be policy decision. And so even though C advertising CAW to X, X will make a policy decision that for the destination in W, I should use path this and not this. And this could be done by local preference. So for any destination here, some destination D, X can have a local preference that for the route BAW, the preference is 10, for the route CAW, preference is 5. So this being a high preference, X will always send. So using the local preference, using the length of AS path, and then looking at the hot potato routing, one could decide how to do the policy-based routing, and that is the key advantage this BGP provides. So we would like to look at why do we need different intra-AS and inter-AS routing. One reason is policy, because my intra-AS routing does not support policy. And one of the key criteria and across the AS is through my to I maintain different things. And as a policy, I got to decide what should be my way I should send traffic. So policy can't be supported by intra-AS routing, hence we need inter-AS routing. Why we don't need the policy decision in intra-AS? Because within the AS, whole configuration by a single admin, and single admin, they all treated it equally, so we don't need a separate policy decision. The policy decision needed across, so we don't need policy in intra-AS, but we need policy decision in inter-AS. Scale, because we are doing the route aggregation, and we are working with the prefix rather than each network, so hierarchical routing scales up, and that is what we do in inter-AS routing versus intra-AS routing. And that means my routing path protocols, because aggregated routes, my length of advertisement, the size of advertisement messages of BGP routes become small, and that way it is beneficial. The key part happens is the performance. In intra-AS, because we have the cost parameter, we can determine which part to be taken based on the cost. With that, we can do load balancing, other things. And we're looking at the cost, we can certainly look at the performance. In inter-AS routing, we don't get to know the cost. We don't know how the route has been arrived at. And that means it may not deliver the right performance because it's currently even optimized. The costs are not comparable. So we're focusing on performance. Intra-AS would perform better, but in terms of scalability and policy, inter-AS routing would work much better. So to summarize, we looked at the inter-AS routing, and we have gone very, very high level, maybe I can say 10,000 feet overview, because BGP as a protocol, it's a very complex protocol, and if somebody want to understand BGP, a whole full semester course can be offered to explain only BGP. It is that complicated. So we're trying to summarize, understand the key concept, the way BGP works, rather than getting into nitty-gritty, because that is not part of it. So it gives you the idea, and those who are interested can look at the BGP RFC, look at the implementations. So most of the autonomous systems use BGP to connect to each other, and that's the reason it is called. BGP is a protocol that glues the internet together, and currently we are in the BGP version 4. So that brings to the end of our discussion today. If any questions, let me know. If no questions, then we can stop. And tomorrow we'll look at broadcast routing and multicast routing. Any questions? If no, then I'll disconnect. And nowadays, I do upload the lecture recordings onto the YouTube. So you can always look at youtube.com/rp. You'll find all the lectures. I'm not sending a link because you can find all the lectures right there. In case you don't find the link within one day of lecture being held, then get back to me, then I'll make sure that is available. So no lectures, I'll stop it, and tomorrow we'll look at multicast and broadcast routing.
Thank you, sir.